All right, this is 11.2 conservation of energy. Today we are going to talk about the law of conservation of momentum and energy. The kinetic energy for potential energy, like you're going to calculate given one or the other, and you're going to calculate kinetic energy doing a collision. So basically what we're going to do is combine momentum, which was chapter 9, with energy, which is 10 and 11. Make sense? It shouldn't be too hard, I hope. Okay, so conservation of energy. Remember that momentum used the conservation of energy in order to conserve momentum. It's very similar. The law of conservation of energy states that energy is not created or destroyed. It is only transferred. When we say energy is lost, we mean that it's not destroyed. It's just transferred out of the system. And whenever it's transferred in or out of the system, that's called work. Because work is a transfer of energy. Yeah.
And you said work is the transfer of energy?
Mm-hmm. So if it's positive work, then the system gained energy, and if it's negative work, then it lost energy. It has nothing to do with direction. It's not a vector, it's a scalar. Okay, so see, is that a blue cup or is that a red cup? It's a blue cup, okay. All right, conservation of energy. So your energy, whenever you're in a conserved system, this means no work is done. So no work is transferred in or out. We were talking about that yesterday a little bit. So that means that all your energy has to equal some sort of total energy at every point, because there's no change in energy. So they should always end up equaling some sort of total. We have like a little example down here. I'll draw it on the board. We have an inclined plane, and you have a ball, and the ball is here. What type of energy does it have when it's up here? Potential energy. So it's not moving, and it's potential energy, gravitational potential energy. Now the ball can either go straight down, or it can go over here. If this is a frictionless surface, how fast would it be going? Well, not how fast. At which spot is it going to be faster when it hits the ground, or right before it hits the ground? Right before it hits the ground. Is it going to be faster at A or faster at B? It's the same. It's the same. It's a trick. And it's because it starts with the same energy. What kind of energy does it have here? Kinetic energy. What kind of energy does it have here? Kinetic energy. So all the energy has to remain the same. So if the energy up here is like 10 joules, there's no work done on the system. So at the bottom, it has to be equal to 10 joules or 10 joules here. So it doesn't matter which way it goes. As long as this is frictionless, it's going to be faster in either place, and they're going to be the same. If there is work done, so if this were some sort of friction surface, taking energy out, let's say the work is finished, that means that it'd actually be going slower at A because some energy would be taken out here where there's no energy taken out over here. So that's the only way it would work. But for your problems for this section, it's conserved energy, so you don't need to worry about this. When you're calculating these things, if you know it's a conserved system, that's what you're going to start with. So you say, oh, it's conserved. And you know this because no friction. No wind resistance. No extra push or pull, no motors, no fins, nothing. And most of your problems will be like that. Most of them will say it's a conserved system, or there's no friction, or something like that. Or they just won't say anything, and you can just assume it's conserved. So if this is true, you say the energy initial is equal to the energy final. So if you're looking at, if this is your initial, And this is your final. Initial is potential energy. And final is kinetic energy. Initial, final. And then you just replace these potential and kinetic with the equations. mgh, initial, 1/2 mv squared at the final position. And then you can solve. So you can get, I know what height I dropped it at, so I know how fast it's going to be going at the bottom. Let's go with one more trickier part while we have it here. Let's say that you want to go from here to here. So this is your new final. Let's call this C and D. Part C and part C. Part D. Okay, again, it says it's conserved, no friction. So initial energy will equal final energy. In this case, we're going to go C to D. I'm just doing a different section. We're going from here to here. What type of energy does it have at D?
Rotational
Pretend that it's frictionless and it's sliding down without rolling. In this case, because we want to make it not so complicated. Okay, so what kind of energy does it have? Potential and kinetic. Good. Because it's halfway down, it has some sort of height, but it's also sliding. And again, pretend it's not rolling. A ball was a terrible plan. But that's okay. It's a box. Pretend it's a box. Okay, so C to D. So at C, we have potential energy at C. And at D, we have potential energy plus kinetic energy. So we do mgh, the height here, is equal to mgh, the height here, plus 1/2 mv squared, well, how fast it's going. So you can figure out how fast it's going if you know the initial height and the height that you're trying to figure out how fast it is. See how much easier this is than like either forces or kinematics, because all you need to know is the heights. Like before, when we did this, we'd have to use a couple of these equations. Okay, so let's talk a little bit more about this. This is pretty much what your homework will look like. I can try to give you a couple of different examples, just initial to final, nice and easy, or one that's like half in the middle from initial to the middle of it. It's always energy is conserved, and then you just put in what kind of energy does it have here versus what kind of energy does it have here, and then solve for your unknown. Okay, so, and that's pretty much what this says. Since energy is conserved, energy is transformed into different types of energy. So in this one, we took potential energy and we turned it into kinetic energy. Your rover took elastic potential energy and turned it into kinetic energy. If we break this initial energy equals final energy up into the different types of energy, we see the kinetic initial plus potential initial equals kinetic final plus potential final. Most of the time, some of these are 0. So in this example up here, kinetic energy initial was 0 and potential energy final was 0. So we didn't even include them into our problem. We don't. When you're looking at the change in energy, the potential energy lost is turned into kinetic. That's what this means down here. It just means that we took potential and we turned it into kinetic. So it lost potential, but it gained kinetic. So the total energy always remains the same.
Ms. Phillips, what did you mean by when you said that you didn't use that energy initial and energy final? When you pointed out that equation, you said that.
Oh, I used initial equals final. I just didn't use kinetic initial and potential final because it didn't have any. It was all potential. 0? It was just 0. So I didn't even bother writing it down.
Right.
So that's like the full equation, and then some of those things are 0, and it simplifies to this. I find that this is easier because you don't have to write as much. You're just looking at, what type of energy versus what type of energy. still see a couple of red cups. So we have a couple of different systems. Roller coasters. Let's give you just a quick picture of what that's going to look like. If you have a roller coaster like this, you'll have some height, call this A, some height B, and some height C. So if it starts up here and it's not moving, what kind of energy does it have up here? Potential. Good. At here, what kind of energy does it have?
It's moving.
Kinetic. Good. Yeah, it should be moving when it's down here. At here, what type of energy should it have?
Potential and kinetic.
Potential and kinetic. If this is a conserved system, initial energy equals final energy, you would go, okay, energy at A is going to equal energy at B, which will equal energy at C. Each question is going to ask something a little bit different. It'll ask you, how fast is it going at the bottom? Well, you can set A equals to B, so you can ignore this part to solve that part. And then it'll ask you, how fast is it going at height C? Well, you can use either one of these because you know the total energy and set it equal to EC and solve. So if you wanted to break this apart even more, you just go, oh, at energy A, mgh at A. At B, kinetic energy, so 1/2 mvv squared. At C, both of them. So mgh at C, 1/2 mv squared at C. And then depending on what you need, you just use that part of the equation. So if you're looking for the velocity here, you can ignore this part. If you're looking for the velocity here, you can either ignore this part or this part, depending on what numbers you have. Because they're all equal. It's like 1 plus 1 is 2, 2.5 minus 1/2, 1. No, they're all equal. Sorry, that's terrible example. Okay, other things that they talk about: skiing, pendulums, and springs. They're all like this. So you're just locating the energy based on its height, and then setting them all equal to each other. Each point's energy is equal to each other. In each of these sections, it's important to choose a coordinate system because of your height. So for this one, our coordinate was 0 is the ground. If we chose this to be 0, then it's going to have a drop in height, so you'd have a negative height. It'll still work. You just have to worry about the negatives. So usually the lowest point on my map, I usually make 0 and everything else is positive, just to make things more simple. Because you can have a negative potential energy. It is possible to have it go below your 0 line. If it goes in a hole or it goes in a well, or you put your 0 line up here, it's okay, it'll still work. You just have to be consistent. And with those negatives, it makes it a little bit more difficult just to follow what it means. All right, are we ready for collisions? Not yet. I still see some red cups. One more red cup. All right. You'll remember the momentum equation that says in all collisions, momentum is conserved. So whether it's inelastic or elastic, whether it sticks together or bounces off or is glancing, momentum is always conserved. So this is mv plus mv plus mv plus mv. For it to be elastic, that means that it does not stick together and energy is conserved. Mostly energy is conserved. That's what an elastic collision means. It means that the kinetic energy is conserved, right? So you have two objects and they hit each other and they go some other directions after they hit each other. So momentum is conserved, but in elastic collisions, so is kinetic energy. This means that if you have two objects that are colliding, you only need to know their initial velocities because you have two equations. You can solve for the two final velocities with these two equations. So if energy is conserved, the first object and the second object are moving. Afterwards, they're moving differently, but their total energies have to be the same. So you can turn this into kinetic energy of the first one plus the kinetic energy of the second one equals the kinetic energy plus of the first one and the second one after the collision. There is a simpler version of this equation down here. I don't remember what it is. I have to look it up. So, I have it in a book somewhere. So while you guys write that down, I'll try to figure it out. It's a much easier equation than that. I don't know how much you're going to actually have to use that equation. There it is. Okay, so if you want to cheat, because that is a pretty nasty equation down there, it actually simplifies into so that's much easier to do. So I would write that one down right underneath this because it simplifies into that. You do need to take direction into account, so if your velocities, one is going this way and the other is going the opposite direction, one of those needs to be negative, and you need to make sure you put that negative wherever it's supposed to go so that you might end up with a negative and make it positive. So just be aware of that. Okay. For inelastic collisions, remember these are the ones that stick together or just lose energy but don't stick together. Your momentum of the first two objects before the collision should equal the last two objects. If they stick together, your masses will be stuck together. Right? So they'll be going the same velocity afterwards because they're stuck together. This is a loss in energy. In other words, energy is transferred out of the system, so there should be some sort of change in energy. And your final minus your initial will be that change in energy. This one doesn't really help you too much in solving these things. You still have to be given the same amount of variables. So you should only have one unknown. But you will be able to calculate the energy loss, which could be a question. So I have a practice, and I think then we're finished. I mean, I have quicker questions on this. It should be pretty much all the information. Let's see if it crashed on me yet. Oh, it's working so well. Okay, we're ready for our practice problem. A 12-kilogram roller coaster starts at the top of a 55-meter hill. It coasts down to the lowest part of the track and then back up to the next hill, has a height of 49 meters. What's this 1,200 kilograms? How about the 55 meters? Height? And the 49 meters? Height. Okay, so we need to draw pictures so we can figure out which height is which. Here's our 55 meters. Here's our 49 meters. We'll call this point A and this point B. Now, wait, one sec. Let's change that just a little bit. Because if you look at part B, it says at the bottom of the track, so we're going to go part B and part C. All right, so what height is this? This one? We'll go with height A. And this one? And C. Okay, part A. What are we looking for? The speed where?
Wait, but I don't think that makes sense because
It doesn't.
the roller coaster is at rest.
It's at rest, yeah. So at part A, this one's at 0. So that's weird. I think I meant to say energy and not speed. Oh well. Okay, part B. What are we looking for? Speed at the bottom of track, so right here, the speed at B. This is a conserved system. There's no friction. Usually your book will tell you there's no friction, but I wrote this problem, so that's why it's so terrible. If energy is conserved, there's no friction. Energy initial equal energy final. For this problem, you can be more specific. Energy at A equals energy at B, which is equal to the energy at C. Anyone have any questions about that part? Because that's how you get started. No, you guys are okay with that. All the energies should be the same. It doesn't matter what part of the track you pick. If you pick this part, the energy here should equal to the total energy there.
So how does that top equation relate to that second one down there?
This is just a general energies conserved equation. Because I have more than an initial and final, because I have an initial and final, and then we start, we go to here, we have more than 2 points. What I'm stating here is that the energy here will equal the energy here, which will equal the energy here. I'm just making it more specific to my picture. Good? Any more questions? This is a good question. That's what I want to make sure you understand. Okay? Now, what type of energy does it have at A? Potential energy. What type of energy does it have at B? And right here is on the ground in this specific problem. How about at C? Kinetic and potential. Okay, so this is A, this is B, this is C, and this is C. Any questions about that? Label what kind of energy it has at each point. Now we're going to plug it in. Now, for this one, we're looking at B, so you can kind of ignore C for now. We'll come back to C in a minute. We don't need it. So at energy A is just potential energy. So potential energy at A. And at B, we have only kinetic energy. Now we're going to leave off C because we don't need it. We just need 2 in order to solve what we're looking for. Okay, we're going to replace potential energy with its equation and kinetic energy with its equation. And then we can solve. Notice that the masses cross out. We can do that right away. You okay with that one?
Oh, the mass.
Okay. No, well, just getting the potential energy and the kinetic energy. I just replaced it with the equation for potential energy and the equation for kinetic. So now we'll plug in our numbers. G is 9.8. Notice there's no negative here. We're not worried about direction. We're just, quantities are fine. The height at A is 55, 1/2 dV squared. So if you want to put it all together, because you're lazy like me, you only want to type one thing in the calculator, you can solve for VV. And we come up with 32.8. Fast roller coaster. Okay, so that solves this. That solves this. This is B. At C, what are we looking for? The speed at the top of the second hill, which happens to be 49 meters. So you're going to look back over here, and it doesn't matter if you start with B or with A. It doesn't really matter. Which one do you want to do, B or A? A. Is that what you said? A? You said B. It doesn't matter. A is easier.
Yeah.
Because B has this square in it and the margin. It's not that much harder, but we'll just look at this part just because this is a little bit easier to solve, but it doesn't really matter which one you do. Energy at A is the potential energy. At C, it is kinetic plus potential. So I got that from my picture. That's why it's important to draw the picture. Now I'm going to replace the equation for potential energy and the one for kinetic energy so that I can actually solve it. There's mass in all of these things, so you can take that out. This would be 9.8 times 55, 1/2 VC squared plus 9.8 times 49. And that's it. And I don't actually have too much more time for quicker questions, so I'll just move on to the homework. So here's your homework. It's the 15 through 21. Make sure you're looking at the bottom for the honors.